Okay, guys. Okay, today I will teach you about the lesson for today is going to be we are actually at the end of the chapter. So the lesson today is about catalyst. Okay, so the catalyst, as you can see here, they are divided into two. Okay, which is known as homogeneous catalyst, and we also have heterogeneous catalyst. Okay, so when we look at okay, let's actually go through this slide is taken from your textbook. Okay, therefore, okay, everything that you have over here, it's from the textbook. So you can see that if you have homogeneous catalyst, okay, the catalyst that we have over there, they are in the same phase as the reaction mixture. Okay, so if you take, for example, okay, if you have this example, okay, this is an ester, okay. So I'm muted. Okay, so it's actually an acid hydrolysis. Okay, this acid hydrolysis will break the ester into its carboxylic acid and alcohol. So you can actually have this carboxylic acid and alcohol over here. So the reason why it is called acid hydrolysis is because the acid that we use over here is going to be the catalyst for this reaction. Okay, this is part of, if you want to know more about the reactions involving ester, okay, you can actually check my video on ester, right? Everything is there. So again, if you want to break this, okay, the catalyst that we use, okay, is going to be the acid. Okay, so this is going to be the catalyst. So if you look at the state, okay, or the phase of the acid, okay, the phase is going to be aqueous. Okay, aqueous. So you can see aqueous, aqueous, aqueous. Aqueous means contains water. Okay, water is going to be in liquid form. So you can see that all of them, okay, in the products and catalysts, they are all in aqueous phase, or they are all in a situation where they have water. Okay, they are all in a situation where they have water. So that is going to be known as homogeneous catalyst. Now, if you look at the heterogeneous catalyst, okay, heterogeneous catalyst is going to be when you have the catalyst, okay, it's going to be in a different phase. Okay, so for example, okay, like if you have a decomposition, okay, of aqueous hydrogen peroxide. Okay, aqueous hydrogen peroxide, if you want to decompose to give you water and oxygen, okay, they will use the catalyst, which is going to be the manganese 4 oxide. Now, manganese 4 oxide, they are in solid form, they are in powder form. Okay, so this one, okay, we call it as a heterogeneous catalyst because this is going to be solid. But if you compare with the rest of the reactant and the products, they are in aqueous, they are in liquid, they are in gas. So they're totally different. They do not follow the same phase as the reaction mixture. Okay, so manganese 4 oxide is in solid phase, and then hydrogen peroxide is actually in the aqueous solution. Okay, so if I give you one example, okay, one example, for example, if you look at Haber process, okay, Haber process, Charlton, can you give me the equation for Haber process?
uh, uh,
Haber process.
uh, N2 plus H2 become NH3.
Okay, so it's a reversible reaction, right? So let's actually balance this equation. Anyway, it's actually quite laggy. Okay, so anyway, it's over there. So let's actually balance the equation. Charlton, how do you balance this equation?
3 on hydrogen, 2 on the NH3.
Okay, so can you give me all the states?
Gas, liquid.
How come ammonia become liquid? All of them are
Aqueous.
gas.
Gas.
Okay, All of them are gas, and you need to memorize by now, yeah, because you're already in A2, yeah. So JC2, you need to know that this one is negative 92 kilojoule per mole. It's an exothermic reaction. Okay, you can memorize. Okay, it's one of the very important reactions in chemistry. Now, can you tell me, Jody, can you tell me what is the catalyst that we use for this reaction?
Iron.
Okay, iron powder. Yeah. So iron powder is going to be solid. Okay, Fe, solid. Okay, can you tell me Haber process? Okay, if you're using iron powder, are they actually homogeneous catalyst or heterogeneous catalyst, Lavi?
Hetero.
Okay, so this one is going to be heterogeneous catalyst. If they ask you what is the reason, how do you explain, Lavi?
The catalyst is in solid phase and N2 and H2 is in gaseous form.
Okay, so or you can say the reaction mixture. In this case, the reaction mixture is going to be, all these are reaction mixtures because it's a reversible reaction. Okay, so all of them are reaction mixtures. All the reaction mixtures are in gaseous form. Okay, but okay, the iron powder is going to be in solid form. Yeah, so we have to refer to the reaction mixture. Yeah. So can you give me another reaction, see, like this, okay, where we can actually discuss about catalyst? Any other reactions that you know that actually have catalyst? Can you recall, Nicole, Trisha, or Arneta? Can you actually give me one more example that involves catalyst?
Contact.
Okay, contact process. If it is contact process, can you give me which reaction that we need to look at? I think when it comes to contact process, okay, there are few reactions, right? For the reaction, I will write down separately first. Sulfur plus oxygen gives me SO2. SO2 plus half O2 is a reversible reaction. It gives me SO3. SO3 plus H2SO4 gives me H2S2O7. This is oleum. H2S2O7 plus water gives me 2H2SO4. Okay, this is actually all the reactions, okay, all the steps that happens for contact process, but only one of the process involves the catalyst. Okay, so since Arneta mentioned that, so maybe Nicole, Trisha, can you actually tell me which of the process over here between 1, 2, 3 or 4, which one will be involving the catalyst?
So is it 3? I don't know.
No,
I,
it's
I
not
don't
3.
know.
It's not 3. So okay, maybe someone else can guess. Shane, can you guess? Take a guess.
4.
No, it's not 4. I think out of those guesses, I think please remember this, yeah, very important. Okay, the one that is actually involving the catalyst is going to be reaction number 2. Yeah, so this reaction, okay, is also combustion. You can see the reaction of oxygen, combustion of SO2, if you want to put it in that way, or oxidation of SO2, okay, to give you SO3. Now this reaction, okay, requires a catalyst, so I just put down the equation over here. So all these, okay, they are in gaseous form. Gas, gas, gas. So can you tell me what is the catalyst that we use for contact process? So maybe Justin, what is the catalyst we use for contact process?
Vanadium oxide.
Again? Vanadium?
Vanadium oxide.
Yes. Or to be exact, is vanadium 5 oxide. Okay, so that is vanadium 5 oxide. So let's actually have Jason. Jason, can you actually put it down as a formula? How do you write vanadium 5 oxide?
V2O5.
Yes. Now, this one I want you to also take note. Now, when you have, okay, potassium, this is totally outside of this, potassium permanganate or potassium manganate 7. Okay, we also have potassium dichromate 6. Okay, when we put this down, whenever you see this number, okay, this is the oxidation number. Now this oxidation number refers to Mn. Okay, oxidation number is +7. This is going to be referring to Cr. Okay, the oxidation number is 6. So when I have vanadium 5 oxide, or before I go there, like for example, if I say iron 3 oxide, or if I say iron 2 oxide, okay, if the oxidation number comes in the middle, it means that this is going to be the oxidation number for iron is +3. The oxidation number of this iron is +2. So they will help us to write, okay, like for example, for iron, I think it's going to be easier. So Fe3 plus O2 minus. So if I want to write the chemical formula for this, okay, this one times by 2. Okay, I think by now you should know, right? Times 2 times 3. So this will be Fe2O3. And if you have iron 2 oxide, okay, it's Fe2 plus O2 minus, both of them are the same. So it's FeO. Okay, so that is going to be for iron 2 oxide. Okay, so similar to that, okay, when we look at potassium permanganate and so on, this one you memorize here. K, normally we write it in this way, KMnO4. Okay, this one is K2Cr2O7, because we know that this is 7. So let's actually try to prove, yeah, whether KMnO4, the oxidation number, whether it's going to be, if you're not sure about this, okay, is it 7 or not, we can actually prove it's 7. Okay, if you're not sure about K2Cr2O7, if for Cr you are not sure whether this is going to be 7, this is going to be +6, let's actually prove it. Okay, you can actually do, okay, you can separate them. Okay, MnO4 minus, okay, separate them. You separate this one, this is Cr2O7 2 minus. Anyway, I hope you actually saw my WhatsApp message yesterday. I think the one that I did for our previous lesson, the one I separated for kind of forget what, nitrogen Br, I think NOBR. Okay, so I think I remember this. Okay, you want to actually find the oxidation numbers for this. Okay, what we do, okay, instead of separating this, because if you separate, there is no such thing as N plus. Yeah, so the one that you're supposed to separate was, okay, this one I put it in the WhatsApp group. If you want to find, okay, if you want to find the oxidation number, you separate here. Okay, you will get NO plus and you will get Br minus. So if you want to get the oxidation number of Br, because oxidation number of Br is always -1. Okay, why? Because it's group 7. Okay, follow the balance. So this is -1. So if you want to find the oxidation number for nitrogen, so similar way, X plus -2 equals to +1, X equals to +1 +2, so +3. So please actually take note. Okay, what I did a mistake where I separated the nitrogen out. I did like this. This is wrong. Okay, please take note. Okay, now coming back, okay, to our lesson today. So here I want to actually prove, okay, it's much more easier to calculate in this way. If I want to actually calculate for Mn, so Mn, so this is going to be x, okay, plus 4 times -2 equals to -1. So if I put x equals to -1 plus 8, I am going to get plus 7. So it's proven. So for Mn is plus 7. So if I want to find out for Cr, so 2 times x, I just put x. So plus 7 times -2, oxygen is always -2, equals to total number, which is -2. So just now was -1. Yeah. So 2x minus 14 equals to -2. 2x equals to -2 plus 14, which is x is going to be 12 divided by 2. You will get plus 6, which is proven over here. So why we are doing this, I just want to show you, okay, if I have the catalyst vanadium 5 oxide, it means that this is the oxidation number for vanadium is 5. Yeah. So if the oxidation number for vanadium is 5, so this one is going to be V5 plus. Okay. So V5 plus, okay, and then you have oxygen is always 2 minus. So if I change my ink over here, okay, this one will be times by 5, okay, and this one will be times by 2. So if I want to write it down, okay, V, so I take this 2, O, I take this 5, okay, that's why it's V2O5, okay. So anyway, V2O5, vanadium 5 oxide, okay, coming back to our question, okay, vanadium 5 oxide is solid. Okay, vanadium, if you look at your periodic table, let me actually show you very fast. Okay, if you look at your periodic table, okay, the position of vanadium, okay, let's actually have a look at the position of vanadium. Yeah. Okay, this is the position of vanadium. Okay, it is under the transition element part. Okay, so do remember, most of the time, okay, I think when we look at the transition elements here, so the transition element, let's actually look at the properties of transition elements. Let's actually discuss on that as well. So when we look at the properties of transition elements, so what can you say about the properties of transition elements, Aneta? Based on your prior knowledge on transition elements, what can you say about transition elements?
More than one oxidation number.
Okay, so transition elements, they actually can have more than one. Okay, one of the important thing is they can actually form more than one oxidation numbers. Okay, multiple oxidation numbers. And then other important things that you can tell about transition metals, Victoria.
Is it like they are colored?
Yes, so they actually form colored complexes. Okay, they form colored complexes. Because normally when we see Fe2 plus, we say Fe2 plus and Fe3 plus. We say Fe2 plus is going to be green. We say Fe3 plus is going to be brown. Okay, so this one is actually caused by the complex, not only the ion alone. Okay, we will learn more. Okay, under transition elements. Yeah. So anyway, this is going to be green, that is brown. So they can actually form colored complexes. Okay. So these properties, okay, the one important over here, the more than one oxidation number, okay, they will actually help out, okay, because they can be always used as a catalyst. Okay, later we will actually look at in what kind of catalyst. I think I can actually also introduce now. You can see that when we look at Haber process, Okay, the iron powder is solid. Okay, and then the rest, all of them are gas, gas, gas. So this is going to be something you are having heterogeneous catalyst over there. Okay, but you know that iron, okay, they are also under transition elements. Okay, so here if you look at because transition elements, you see iron can actually form Fe2 plus, Fe3 plus. Okay, and if you look at other examples, like for example vanadium is also a transition metal. And then they also here in contact process. Okay, let's actually see whether someone can answer. Maybe Gabriela Nicole. Okay, if I use vanadium for 5 oxide, which is solid, okay, what kind of a catalyst is this? Is it heterogeneous or homogeneous catalyst?
Hetero.
Yeah, so it's a hetero. So you can see that generally, okay, generally the transition metals, okay, they always form, or they are very good, okay, being used as catalysts, especially if they are in heterogeneous catalysts. Okay, we will learn more about this. Okay, so they tend to actually use transition metals for heterogeneous catalysts. Okay, so coming back here now. Okay, so this is going to be the, I think the introduction, you know, is kind of a, okay, catalyst can be divided into two. Okay, you can have, okay, but the idea is, okay, the catalyst, the homogeneous catalyst, okay, they must be, okay, the same, in the same phase as a reaction mixture. Heterogeneous catalyst, they must be at the different phase as the reaction mixture. Okay, so can we actually have someone to summarize this slide? Okay, Jody, can you summarize this slide? What you learned from here?
Homogeneous catalyst, all the state the same.
Okay.
Then if heterogeneous catalyst, the catalyst and the reactant and product not the same state.
Okay.
And then
so if I actually put it
transition.
in this way, Jody, I'll just stop you for a while. Okay, so Jody, if I put it in this way, if I ask you, of course you can actually understand the concepts and so on, but if I ask you to recall the reactions, for example, if you have homogeneous catalyst and I have heterogeneous catalyst, okay, if I ask you to give two examples, okay, two examples of reaction involving both of them, so can you actually give that? Like for example, how do I know, like give me one example, homogeneous, okay, reaction, okay, homogeneous catalyst. You have 4 equations. Can you actually, the Haber process will come under where, Jody?
Haber process hetero.
Okay, so
Yeah,
I'll
hetero.
just write down for you. This is going to be heterogeneous catalyst. Sorry. Okay, while waiting, you can actually decide on the others. So this one is going to be Fe, solid. The rest is all gas. Can you give me another heterogeneous catalyst? I think I gave 3.
Contact process.
Okay. So the contact process, so sulfur dioxide plus half O2, SO3. So all of them are gas. And then you are using vanadium pentaoxide, solid. Okay. I think there was another one that I actually mentioned as well. Under heterogeneous. I think this one, I think I only mentioned one. One more. It's inside the slide just now. Can you recall?
Forget it.
Hydrogen peroxide, the decomposition to give you O2 and water. What is the catalyst? I think Justin, you can answer this. What is the catalyst?
Manganese oxide.
Yeah, so MnO2, manganese 4 oxide. Yeah, so this is going to be solid. So you can see, Okay, these are the reactions involving heterogeneous catalyst. So if I just want to actually look at the homogeneous catalyst, okay, can you give me one example of homogeneous catalyst, Gabriela Nicole? I think in a simple form, if you have ester plus water, okay, when you have H plus, okay, where they give you alcohol and carboxylic acid. Okay, so this one is aqueous, okay, aqueous, liquid, aqueous, aqueous. So that this one is going to be one example of homogeneous catalyst. So this is the summary actually, okay, based on the concept, and I want you also to remember what are the types of reactions, okay, what are the examples of reactions for homogeneous and heterogeneous. Yeah, so I will go on, okay, I will move on. So let's actually go and look at the homogeneous catalyst, okay. So let's actually go in detail about how they actually work, okay. Now, homogeneous catalysts, okay, they work, okay, whereby the principle is more towards, okay, involving the changes in oxidation number. Okay, that is going to be the principle of it. Okay, they will work in such a sense that they will involve the change in oxidation number. Okay, uh, one of the reaction over here that they have mentioned over here, this one, okay, they put I minus, okay, they put I minus, okay. I think just now when they give us the equation earlier, they say it's MnO2, okay, they put MnO2 for the reaction. So here in the textbook, okay, they still put I minus, okay. I think this is going to be another type of catalyst also, okay, to change, okay, to change hydrogen peroxide into water and oxygen. Okay, so there is another catalyst. Okay, so do remember, okay, the conversion of hydrogen peroxide, okay, the decomposition, you can either use the catalyst, which is going to be MnO2, or you can also use I minus, okay, in this case. Now they put I minus, and you can see the I minus is actually in aqueous form, okay, aqueous, okay. The reaction mixture, okay, which is H2O2, they are in aqueous. I minus is also in aqueous, therefore they are going to be homogeneous catalysts. So what actually happens, okay, the principle behind it is, okay, it involves changes in oxidation number. Let's actually see what is the changes, what are the changes that is going to happen. Okay, when I have H2O2, when they react with I minus, what is going to happen, okay, is the oxygen, okay, from here, the H2O2, they will actually go out, and they will actually form, okay, a bond with I minus to form IO minus. Okay, this thing is going to be formed. Okay, so this is going to be some sort of an intermediate that is being formed. Okay, this intermediate, okay, it will be destroyed, or it will be eliminated. Okay, it will be eliminated in the second step, where, okay, the H2O2, they will actually react with the intermediate IO minus, and they will give you more H2O and further form I minus. At the same time, they will give you O2. Okay, so this step, it involves two steps over here. Okay, when we write the overall equation, it means when I add these two equations together, what is going to happen? Okay, this and this will cancel. Okay, I minus and I minus will cancel, and I am going to get 2 moles of H2O2, gives me 2 moles of water, and give me 1 mole of oxygen. Okay, so in this case, okay, the catalyst that you put, okay, the catalyst that you put, okay, they appear that they don't get used, but they do get used. It means there is a chemical change. Okay, there is a chemical change. okay, whatever things that you learn in the past that they do not take part in the reaction, actually they do take part in the reaction. Okay, but okay, at the final state, okay, the whatever that catalyst that you put, you will get it back, but maybe in a different physical state. Okay, different physical state. Okay, so here, okay, this is going to be the role of the catalyst, in to be exact, the homogeneous catalyst, okay, of I minus. And then if I ask you which one is the catalyst over here, okay, this one normally I put it in a PowerPoint slide, okay, but the answer is already there. Okay, if I ask you which one is the catalyst for this reaction, okay, the catalyst is going to be I minus. Okay, but if I ask you why, okay, Gabriela Lavi, why I say that I minus is the catalyst over here? What is the reason? Why not IO minus? Why I minus?
Is it because it loses the oxidation number?
Actually, that is the explanation. Okay, that is the explanation. I think, let's say, if you want to identify catalyst, I think we go into the definition of catalyst. Catalyst is being used in a small quantity to increase the rate of reaction. Okay, it is used in a small quantity to increase the rate of reaction, and they do not take part in the reaction. I think last time you actually learned about this. Okay, it means you put, then they come out. Okay, it means they don't get consumed, okay, by the reaction. Okay, it means they are not reactants. Okay, but they do react. Okay, this one I want you to learn. Okay, they do react, but they appear they don't react because you put, and then the product is also going to be the catalyst. It means they appear that they don't react. So in this case, the only thing that appears that don't react is I minus, because I put I minus and I am getting back the I minus. Okay, I put in aqueous form, I am getting it back in aqueous form also. Okay, that is the reason why IO minus is not a catalyst, because I'm not going to get the IO minus. It's going to be disappearing. Okay, I didn't put IO minus, and at the same time it's not actually being you cannot obtain that IO minus also. Okay, so that's the reason. Okay, but if you want to look into detail, okay, what actually happens, okay, the thing that actually happens is the I minus is changing into IO minus. This is going to be the changes of oxidation number, which is the oxidation number of I is going to be -1 here. And if I want to find the oxidation number of this I, is going to be x minus 2 equals to -1. So x equals to -1 plus 2, you will get +1. Okay, so you can see from -1 to become +1. Okay, and that is going to be, they are going to be oxidized. And you can see here, okay, the I is already +1. Okay, I already calculated. So this one will become -1. So now they are going to be reduced. So first, they will undergo oxidation. Then after that, they undergo reduction. Okay, so that is going to be the way how homogeneous catalysts work. So here, okay, I'll give you another example, okay, of how homogeneous reaction catalyze a particular reaction. But before I go into there, I will also write or add more data here. Homogeneous catalyst, can you write down another one reaction that we just learned, Charlton? Can you give me another reaction for homogeneous catalyst that we just learned just now?
2H2O2
I think it's over here. You can actually just check over here. So H2O2
plus plus
come.
I minus the catalyst.
Okay, you are writing the entire thing. Actually, I don't want the entire thing. Yeah. So actually, it gives you O2 and H2O. Okay. So again, this one is
Ah.
going to be aqueous. Okay, they are going to be gas. This one is going to be liquid, but I use the I minus. Okay, but of course, if you want to write the full equation, of course you can do that like just now. If you have the H2O2, when they react with I minus, okay, what's going to happen? You are going to get H2O plus IO minus. And then the next is H2O2. They will react with the IO minus to give you H2O plus O2 plus I minus. So this is what you are going to get. Yeah, step 1 and step 2. So all of them, okay, are aqueous. Okay, you can actually put it yourself. Yeah. So coming back to our lesson again. So if you keep on going, like for example, now if you have iodine peroxide disulfate reaction, okay. So this one, okay, if you don't want to know what is this one is called persulfate ions. Okay, persulfate ions is S2O8 2 minus. Okay, this is persulfate ions. Now these persulfate ions, okay, the reaction, okay, they will oxidize iodide ions to iodine, okay, iodine. Now, so the reaction is very slow. Okay, the reaction is very slow. So they will react with this to give you this. So this is going to be oxidation reaction. Um, to be exact, yeah, let's actually see whether it's redox reaction. Yeah, -1 to become 0. So this is going to be oxidation. So let's actually see from here to here, is it reduction? Okay, I can calculate. S2O8 2 minus, so 2x plus -8 times 2. 8 times -2 equals to -2. 2x minus 16 equals to -2. 2x equals to -2 plus 16. X is going to be +7. Okay, so this one is going to be +7 for sulfur. So SO4 2 minus, SO4 2 minus, x minus 8 equals to -2, x equals to -2 plus 8, you get +6. So you can see that reduction. So Charlton, is this redox reaction?
Yes.
Okay, because it involves both oxidation and reduction reaction. Okay, so Arneta, if I ask you from this reaction, which one is the oxidizing agent?
The oxidizing agent is persulfate.
Okay, something that will oxidize others, but they will get reduced. So this is going to be persulfate. S2O8 2 minus is going to be the oxidizing agent. So now, okay, please actually take note. This reaction, okay, is going to be a very slow reaction. Okay, and why it is a very slow reaction also, you can see that, okay, I'll try to erase all this now. You can see that, okay, let's say you guys tell me, Janice, can you tell me why this reaction is most likely slow? Just think, why you think that this reaction is most likely slow? Is there any particular reason? Can you see the charges? Can you compare the reactant charges? What are the, Janice, what are the charges for the persulfate and iodide?
-2 and -1.
Yeah, both of them are negative charges. So when I actually have two reactants with negatively charged and then I expect to bring them together, expect them to react, okay? Do you think the reaction will happen in a proper way, Janice?
No,
Why?
mm, because it's negative and negative.
Yes, opposite charges, they tend to repel. Okay, they tend to repel automatically. So what we can do, okay, here they say that in order to collide and react, okay, they need to have certain amount of energy so that you can overcome the repulsive forces, because they will have repulsive forces. They don't want to actually come near to each other. Okay, but you need to force them, whether they like it or not. You need to force them. Okay, you need to force them, and that forces can require energy, because you want them to actually go close to each other. So you need certain energy to overcome that repulsive forces. Okay, and those energy, they come from, okay, the reactions. Okay, there are two reactions that's going to happen. Okay, the reactions are, okay, instead of just making them to react directly, what we are going to do is they are going to use, okay, iron 3. Okay, they use iron 3. This iron 3, okay, they will react with I minus. Okay, and this I minus will change into I2, and at the same time the iron 3, they will change into iron 2. So you can see from +3 to become +2, this is reduction. And this is -1 to become 0. Okay, that's going to be oxidation. So there is a redox reaction that is taking place here. And what is going to happen next? Okay, the next step, okay, because now I already have I2. I already have this. Okay, it's not showing on the screen, so it will show a bit late. Yeah, you can see I already have this. Okay, the I2. So now I only need to change the persulfate into SO4 2 minus. So what I can do, okay, you no need to do anything, you no need to add anything, because the moment you add Fe3 plus, the Fe2 plus is going to be formed. The Fe2 plus, okay, what they will do, okay, they will react, okay, they will react with S2O8, okay, persulfate ion, and they will actually change, okay, into Fe3 plus. So again, there is going to be, they are going to be oxidized. And here to here, okay, just now I think we have calculated, okay, I forgot the numbers. Okay, let's say this one is 6. Okay, this is 6. I can quickly calculate -16, -2, 2x plus 7, yeah. So this is +7 to become +6. So this is reduced. So here, basically the Fe3 plus is changing into Fe2 plus. Then that Fe2 plus is going to react with the persulfate, and then they will actually give you the sulfate and Fe3 plus. It means now you are getting back the Fe3 plus. So that is going to be your catalyst. Okay, that is going to be your catalyst, and the ability of those that catalyst to change the oxidation number, it makes it useful for this reaction, because they are involved in both of the reaction. Yeah, they involve the Fe2 plus that is being produced. They will react, okay, with the S2O8 2 minus. So this will prevent, okay, this will prevent the I minus and S2O8 2 minus to react with each other. Okay, it means that there is a reaction, but the reaction is proceeding in a different way, because again, you can see the reaction is more towards plus reacting with something that is negative, plus reacting with something that is negative. So you are having the enough energy for the reaction to happen. Yeah. So this is going to be a very special type of reaction. Okay. So if you put in this reaction, if this is energy profile or energy level diagram, okay, if you see that this is going to be uncatalyzed reaction, okay, without any catalyst, okay, we will get something like that, the one that I draw just now. But in this case, because the catalyst is going to happen twice, it means the one that is going to be catalyst is going to be this one. Okay, Fe3 plus is catalyzing the reaction, okay, for reacting with the I minus. So there is one, okay, one time. And then you also have this reaction, okay, which is going to be another catalyzed reaction. So this is going to be when Fe3 2 plus, okay, is reacting with the S2O8. So there is going to be two bumps over there. This is very important. What does it tell us? Okay, it tells us that, okay, the product of the catalyst, they will also get involved in catalyzing. Okay, the product of the catalyst is involved in the catalyzing. And the important thing that you need to take note for this reaction, any kind of reaction that can come between the E values of both. Like for example, I know I have the I minus. So if you actually have the E value 0.54, and then this is standard reduction potential. So if you have 2.01, anything that comes in between them, okay, from 0.54 to 2.01, they are capable to react. Okay, they are capable to react, or they are capable to catalyze this particular reaction. Okay, so many information. Okay, so many information from this one particular slide. Okay, please take note. Yeah, so if I actually put this again, okay, in a note here, okay, we did study another one, which is going to be another homogeneous reaction. So can you actually tell me what should I write? Maybe Janice, can you help me out? Is a homogeneous or heterogeneous?
Homogeneous.
Homogeneous. So can you tell me what is the one that we just learned? Persulfate. So persulfate S2O8 2 minus. They will
Plus
react with
2
Fe
I
plus. Oh, sorry. Is it I or Fe3 plus?
I and 2 I minus.
Okay, okay, I'm wrong. So it's actually going, okay, you mean this one. Okay, you're talking about this one. So here, in this case, I want to actually write these two, the one that are earlier that Charlton wanted to write, but it's okay. I'll actually write this one first then. Okay, so let's actually write that one first. Okay, go ahead. So it's I minus to give you SO4 2 minus plus I2. Okay, the catalyst that we are going to use over here, there is two types of catalyst, Fe2 plus and Fe3 plus. I'll just put it down over there. Okay, and all of them are in aqueous form. Aqueous. So here, if I want to actually put it down like what we actually did just now, okay, for this reaction. So let's actually write down for this reaction now. So S2O8 2 minus, and then you have I minus. Which one will react first? I think this one will react with Fe3 plus. They will give you Fe2 plus. Okay. And this one is going to be, this one will be reduced, this one will be oxidized. I'll get something like this. So Jason, can you actually help me out with the second one? This will react with Fe2 plus to give me Unmute, unmute. Still waiting for your answer.
Fe3 plus and
Yeah, correct.
SO4.
Plus Fe3 plus. Okay. So I think if you balance it, you just put 2 there. Yep. So you are going to have this reaction. Okay. So you can see that, okay, the Fe3 plus is being formed again. Okay. So if I actually want to actually just write 1 also, still okay. I can actually write Fe3 plus is enough. But in this case, you can see that the catalyst, there's 2. So if I want to actually write the energy profile diagram for this, okay, because it's going to be a 2-step reaction. So for example, if it's like this, okay, we expect to have something like this. Okay, 2 activation energies. Okay, 2 activation energies. So that is going to be what I wanted to teach you today. So of course, I don't want to actually move more, okay, because we will learn more about the heterogeneous catalyst in the next lesson. So that is the part for the homogeneous, okay, homogeneous. And the last part that I mentioned about for this particular reaction, okay, they need to come, the E value must come in the middle. Okay, it will be suitable if it is going to be in the middle. Okay, so Fe3 plus, okay, in this case they are suitable because they are in the middle of this. Okay, so please take note. Okay, we will actually just I think going through this one is quite easy also, but I don't want to rush things off. Okay, we can actually finish this on Monday. Okay, we can finish on Monday, and we can after Monday, on that Monday itself, okay, I will start with a new chapter. Okay, so only one more. I think this one you also can read. Okay, this one is a catalyst is going to be something where you are going to have like, okay, the adsorption, okay, bond to the surface. Okay, okay, you can see from this diagram how the catalyst actually works. Okay, heterogeneous. So you will have like something like it will provide a suitable place for the reactants to bond, and then they will actually kind of break the bond between each other. Okay, break the bond, okay, broke the bond. Then they will start to form new bonds, and then they become desorption. They will remove or detach, okay, from the catalyst and just move away. So this one is generally how the heterogeneous catalyst actually works. It provides, okay, it provides some kind of the area. Okay, it provides an area. I think I can finish it today itself. Let me just finish it today. Yeah, now it always involves gaseous molecule reacting at the surface of the solid catalyst. Okay, for example, nitrogen gas with hydrogen gas, okay, to produce ammonia. Okay, you have these gases. Okay, so we are going to actually react to the surface of the solid, in this case iron powder. So the mechanism can be actually used by theory of adsorption. Adsorption and absorption, they are different. Yeah, so adsorb means bond to the surface of the substance. Absorb means you move right into the substance. Okay, so this one we are talking about bonding on the surface. Okay, the bonding of to the surface, we are going to use the term adsorb. Okay, adsorb, not absorb. Okay, adsorb. Now this adsorb, what is going to happen? Basically, those hydrogen and nitrogen, they will come and diffuse to the surface of the iron, the catalyst over there. Okay, and then they will attach. Okay, they will attach to the surface of the catalyst. So that is going to be known as adsorption. Okay, so the absorption is going to be the reactant molecules are chemically adsorbed on the surface of the iron. The bond are formed, okay, so that it is strong enough to weaken the covalent bond and weak enough to break and allow the products to leave the surface. It means now the bond is quite strong. Okay, the bond between the surface of the catalyst and the reactor are quite strong until this bond between hydrogen and hydrogen can be broken, nitrogen and nitrogen can be broken. And once you have new bonds being formed. Okay, this bond is actually kind of weak enough so that they can go out. It means they can break free from the catalyst. Okay, so that is what we call desorption. Okay, diffusion away. It means simple terms is they come diffused to the catalyst. They get adsorbed. Breaking bonds will happen. New bonds will be formed, and then the bonds with the catalyst will be weakened. We call it desorption, and then they will diffuse out. I think simple as that. Okay, so the part that we actually use a lot of time to discuss is more towards, okay, the homogeneous. So in simple form, I actually finish it. Okay, that's why I told we no need to waste a lot of time. So if you put it as heterogeneous, only this, okay, only the part that we actually just did. So here, okay, if you summarize everything up, okay, if you summarize everything up, how many reactions that we have learned under this catalyst here. So the heterogeneous, we have 1, 2, 3 reactions. For homogeneous, okay, we have 1, 2, 3, okay, 3 reactions. Okay, let me actually check. Okay, 3 reactions. Yeah, only 3 reactions. So 3 and 3. Okay, I want you to really focus on this. And plus, okay, the reaction 2 and 3, yeah, how they actually work. Okay, please actually go through, okay, the involving the oxidation number. So please actually go through this. Okay, yeah, I think that's all. I think please go through your textbook, please finish up, and then probably the recording for the lesson, I will do another recording on Monday. Okay, so that we can actually go through all this and then we can summarize. Okay, any questions before we leave?